Alright, so we have 3 examples left that we're going to work through, continuing on from the ideas that we had yesterday. Let's see. So we were applying theorems in calculus, so you may need to refer back to this, the 4 theorems that we had written definitions about. But we're going to be using those and applying these to these problems. Alright. The total order in transportation cost C of X measured in dollars of bottles of Pepsi Cola is approximated by the function, and they list the function right there. So that's the one that is approximating the measure in dollars. Where X is the order size and number of bottles of Pepsi Cola in hundreds, answer the following questions. First things first, let's make this look a little better. If we have, let's try to make this one common denominator. It may help us later for some of the problems we have. So how can I make that one common denominator? How can I simplify that a little bit? What would I need to do to each of these? This side I would need to do what? And over here I'd have to? Okay, so if you simplify, it's going to end up being x squared plus x plus 3 over x squared plus 3x. Alright, so let's go ahead now and look at our problems. Part A. Is there guaranteed a value r on the interval 0 to 3 such that the average rate of change of cost is equal to c prime of r, the first derivative at r? Give a reason for your answer. So think about the stipulations, think about your interval, think about exactly what they're asking for. It's going to be one of those theorems that we had a definition for that we're trying to apply. Once you figure out what theorem it's trying to apply, does it work or does it not work? And what's your reasoning? So it's talking about guaranteeing some value r on the interval such that the average rate of change cost is equal to the derivative at some r value. Give a reason why it does or does not work. If you're not sure on a reasoning yet, do we at least have a theorem that we think we're going to be using? Remember, you can look back to that first page if you have to. We wrote all the definitions down. Alright, let's see what it's saying. So Rolle's theorem, it talks about a closed interval. Does it mention anything about an average rate of change? Yeah, the mean value theorem talks about an average rate of change. So what stipulations go along with the mean value theorem? What do we need to know? What has to be true? Yeah. Okay, so let's check and see if it's continuous. Our interval's from 0 to 3. And we're including 0 and 3. If we're including those, are there any values that would make this discontinuous? 0. Since c of x is undefined at x equals 0, c of x is discontinuous on closed interval 0 to 3. So the mean value theorem doesn't apply. it doesn't guarantee that there's some value r where it would be equal to the average. So it doesn't apply. We can't guarantee anything. And that's it for part A. We can't guarantee it. Part B. Is there a value r on the interval -3 to 6, or 3 to 6, sorry. 3 to 6, so we have a new interval, such that the derivative at that value is equal to 0. Give a reason for your answer if such a value of r exists, and find the value of r. So what theorem do you think we're talking about here, and does it or does it not work? I think I heard something over here. Rolle's theorem, because we're talking about the derivative being equal to 0. So we have to check and see if it's continuous and differentiable. On those values, can you plug anything in, and will you get a value out? Or do any of those make the function undefined? Those all seem to work. If we were to take the derivative, it seems like it's going to be differentiable. I don't see anything that would cause it to not be differentiable on 3 to 6. So let's go through it, and we can actually look at the derivative in a moment. So since c of x is continuous on 3 to 6 and differentiable on 3 to 6, open interval. And, well, I guess we have to check this because we didn't confirm it yet, so we don't know for sure if it does work yet. The endpoints have to be what? They have to be equal. Let's see if they are. So c of 3 has to equal c of 6. So let's see if they equal the same thing. So go up to your original, evaluate it at 3, and evaluate it at 6, and see if you get the same values. Take a moment to do that, please. Did we find a value yet? Yeah, we get 8,333.333. They are both the same. So since it's continuous, differentiable, and both endpoints are the same, Rolle's theorem guarantees a value r on the open interval 3 to 6 such that c prime of r is equal to 0. So it guarantees that. So we can find what the actual derivative is. We have a coefficient, we can pull that out. So let's go back up to our simplified version. How do we find the derivative of this? What rule do we need to use? How do we find the derivative of this fraction? Quotient rule. Does anybody remember quotient rule? There's a saying to it. Yep. So we have low d high, x squared plus 3x times the derivative of the top, 2x plus 1. So x squared plus 3x times 2x plus 1 minus high d low and then you square the bottom. So I've been looking for the answer on the calculator. I tried to check it earlier. My calculator was giving me issues. I think I may have found where the mistake is, but you should be able to graph this now. And you should be able to find, since Rolle's theorem applies, where this is occurring. And like I said, my calculator was giving me issues, so I'm not sure what is going on with it. The window I was using was giving me a lot of issues. But after graphing, so you can try that if you'd like, and we can go back to it if we still have trouble with it. But let's get the answer down. After graphing c prime of x on 3 to 6, c prime of r equals 0 when, oh sorry, I'll move that up. After graphing c prime of x on the interval 3 to 6, we know the derivative equals 0 at some point r. Well, that r value that we find is 4.098. So that's the value between 3 and 6 where the derivative is equal to 0. Now, like I said, we can go back if we have time at the end of class, unless your calculator was working, but mine was giving me a lot of issues with this problem. And I don't know, there's a lot to type in, so I don't know that I may have typed something wrong. I don't know, has anybody tried it yet? Typing it in yet? Graphing or no? So if you guys are okay with that, we can come back at the end of class if we have time to that. That way we can get through the other examples, and then we can try to mess with the calculator and try to mess with our window. Okay? So this is the answer for it. We'll come back and try to mess with that graph a little bit later. Now for the interval from 3 to 9. What is the greatest cost for order and transportation? So again, we're talking about this interval. We want to know where the greatest cost for order and transportation is. Well, we have these two values to check. What other value do we need to check in this interval? What other value within this interval should we check? Yeah, so we need to find c of 3, we need to find c of 4.098, and we need to find c of 9. Those are the three values that you need to find from the original function. So take a moment with your calculator, you type those into the original and find your amounts. We want to find which one would cost the most. Did anybody get any of the values of the original? What did you get for C of 3? Well, didn't we already find C of 3 above? C of 3 we found up here for the endpoints. 8,333.333. Anybody find any of the other two? Anybody? Vinny, did you have one of these two? Either the 9 or the 4.098? 8,611.111, is that what you said? Yeah. Okay. 8,611.11111. Anybody have the C of 4.098? Braden, did you find that one? 8,213.7. Okay. I have 8,213.672, so yeah, it rounds 0.7. Okay, so all they're asking for this interval, the greatest cost is, what's going to be the 8,611.111 when x is equal to 9 on the interval. That would be your greatest cost. Just asking, when is it the most? Looking back up at this derivative, again, I said if we have time we'll go back to it at the end of class, but I think part of the derivative is wrong, is where I may have gone wrong before. If it's low, d high, that makes sense, minus high, d low, what should the derivative of the bottom be? 2x plus 3. So we'll fix that, and maybe we'll try that again later. And then the bottom squared. Okay. So if we have time, I think we should have plus 3 there, but that's a lot to type in, so we'll check that at the end. Okay. Let's go to the next example. Alright. Again, we're trying to apply the theorems that we talked about. So, a car company introduces a new car for which the number of cars sold, S, is modeled by the function given below, where T is the time in months. Okay, let's go ahead. Let's rewrite that one again. It would be the same as writing 300, and it would be 5T. Let's see. What would the top be? Yeah, 5t plus 1 is what it simplifies to. You have to multiply this by t plus 2, so you have 5t plus 10 over the t plus 2. So you're left with 5t plus 1. That's how you get this over here. Okay. Part A. Find the value of s prime of 2.5 using correct units. Explain what this value represents in context of the problem. Well, if we want to find that value, we need to find the derivative. So we can go ahead and do that now. I think we're going to need it later in the problem. So, again, we have quotient rule. So we're going to pull that out in front, the 300, low d high, minus high d low, all over the bottom squared. T plus 2 times 5 minus 5t plus 1 times 1, because the derivative of the bottom becomes 1, over t plus 2 quantity squared. Okay. So what they want to actually know is they want to know what this is evaluated at 2.5. We want to know what is the value of the derivative at this point. And we want correct units. And we want it represented in context of the problem. So if you evaluate s prime of 2.5, go ahead and take a moment to find your answer. S prime of 2.5. Let me know when you find the value at 2.5. Garrett, did you have any luck back there finding it? Alright, I don't think that's quite what I got. Did anybody get what he got, or did you guys get a different value? Plugging 2.5 into the derivative. Stevie, you shook your head. You got the same answer or a different answer? What'd you get?
I'm going to be wrong. I got negative 148.15.
Negative 148.45. Okay, so I don't think those are what we need. Let's think about this again. Find the value at 2.5. So we're trying to find the cars sold. The units would be cars sold a month. Ariana? 2.1. Not what I have. Let's hear it, Braden. Everybody's giving a try.
0.44.
No, that's not what I got. That's what I'm looking for. 133.333. So if you take the derivative and you plug in 2.5, make sure you follow your order of operations correctly. Make sure you add this, then multiply by 5. Make sure you do these parentheses. And make sure you combine the top and then divide. And then yes, everything is multiplied by 300. So maybe that's where you missed a step. Does it work now, Braden? Okay. So it should be 133.333. And what are the units? We're finding what? Again, remember this is a derivative, it's a rate.
Cars per month squared.
Cars, well this would just be cars sold per month.
Yeah.
This isn't necessarily months squared. This is just cars sold a month.
That was the last one.
Yeah.
Squared part.
We're just asking what the rate is. So, in words, at 2.5 months, the number of cars sold is increasing at a rate of 133.333 cars sold a month. So as a description, if they ask you to explain, that's how you would. At 2.5 months, the number of cars sold is increasing at a rate of 133.333 cars sold per month. Alright, let's go ahead and look at letter B. Find the average rate of change of cars sold over the first 12 months. Indicate correct units of measure and explain what this value represents in the context of this problem. Find the average rate of change of cars sold over the first 12 months. So we want to find the average rate of change. So how do we find an average rate of change? Okay, we're taking the average over a point of time. We're going to use the slope of the secant line. So that's given 2 points. Well, we know we want first 12 months, so our 2 points would be what? S of 12 and what would be the two endpoints? 12 is one of the endpoints. What's the other one? 0 at the very beginning. So we need to find S of 12 minus S of 0 over 12 minus 0. Now again, why do we know we can do this? Well, the only thing that would make it undefined would be a -2, and that's not within the interval we're talking about. So we need to actually evaluate. You're going to have to find the value of S12 and the value of S0. I'll do the bottom. 12 minus 0 is 12. You guys do the top. Again, you should get some value minus a value, and then we'll figure out what our final answer is. If you want to check your answer, I got 1,307.143 for the first one, minus 150. And if you simplify all of that, can you tell me what your final answer is? Subtract and divide. $96.429, and what are the units? Cars sold per month. Exactly. So we're saying that's the average rate of change over the entire interval. Part A was the rate of change at a specific point. So this is the average rate of change in general. So we can say for the first 12 months, on average, of 96 cars were sold per month. For the first 12 months, an average of 96 cars were sold per month. Alright, so not too bad so far. Let's look at letter C. Is it possible that a value of C for the interval 0 to 12 exists such that the derivative at that point is equal to the average rate of change? Give a reason for your answer. If such a value C exists, find the value. So applying those theorems from the front, which theorem do you think they're talking about, and can we apply it? Hint, it is one of the theorems we've already talked about today. You have an answer, Dan?
Yes.
Okay.
I believe it is the mean value theorem.
And can it apply?
Yes.
Yeah. So since S of t is continuous on the closed interval 0 to 12 and differentiable on 0 to 12. The mean value theorem guarantees a value C on 0 to 12 such that S prime of C equals S of 12 minus S of 0 over 12 minus 0. Again, that's what we did up above in part B. So we're saying the mean value theorem guarantees that we can do what we did up above and it will be equal to the derivative at some value. So again, we have, let's see, we have the derivative from up above. We already have that. S prime of t equals 300. I'm not going to write it out down here yet since we have it up above. So you have it up in part A there. Let's see what they're going to ask us. So we need to show that these are equal to each other, but we need to find a value of t. So let's see. We can multiply the top altogether to simplify it a little bit. So if you think of your derivative with the 300 and we multiply everything up top, what are we going to get the top to simplify to on our derivative? S prime of t. And you said what? Okay, if you don't multiply in the 300 yet, yeah, the top is going to simplify to 9 over t plus 2 squared. If you multiply in the 300, you're going to get 2700 over t plus 2 squared. Again, that's just the derivative from up above. Here we go. Just a simplified version of the derivative. And we said by the mean value theorem, we can take that derivative, 2700 t plus 2 squared, and can set it equal to this, the slope of the secant. Well, didn't we already find the slope of the secant in part B? So we don't have to do that over again. Don't do double the work, just take your answer from up above, 96.429. We're saying the slope of the secant is equal to that tangent at that point. So we're trying to find out what that point is of the tangent line. So again, here is where you need to go and solve. So we would have, if you multiply to the other side, t plus 2 squared, and divide that over 2700 divided by the 96.429. I think actually, let's see, 2700 is really close to what number? We'll round this number since it's very, very close. If you divide these two. Does anybody know what this is close to if you divide it? Ryan, did you divide those? What'd you get? Yeah, it's very, very, very close to 28. So we're just going to write 28. I want to square root both sides to get rid of the square. So I'm left with t plus 2 equals plus or minus square root of 28. So my t value is equal to negative 2 plus or minus square root of 28. Now again, our t value needs to be the number of months. T is the time in months. So evaluate both of these and see what answer we get that makes sense to have a time t in months. T should be equal to what? Find the actual decimal answer that makes sense. Again, you're going to get two answers, but I don't think they both make sense. So, what is your answer that makes sense for time and months?
3.2.
3.2, yeah, 2 0.92 months. That is the number of months where the derivative is equal to the slope of the secant line. Alright, so don't pack up quite yet. We have a couple minutes. But that's where we're going to end with the notes. I want to look at something else quickly.